Nenomatica, where mathematics meets YouTube excellence. Welcome to this math video, where we'll explore an important theorem in basic inequalities. This theorem relates to the arithmetic mean geometric mean inequality, but with a specific focus on a number and its reciprocal. Let's start with the first part of the theorem. If it is greater than 0, then a plus 1 over it is greater than or equal to 2. Let's prove this first part of the theorem. We'll start by considering the expression a minus 1 squared is greater than or equal to 0. This is true for any real number, because the square of any real number is always non-negative. Next, we can expand this expression to get a squared minus 2. A plus 1 is greater than or equal to 0. Now, let's divide both sides by a. Remember, since we specified that it is greater than 0, we can divide both sides by a without changing the direction of the inequality. This gives us a squared over a minus 2. A over a plus 1 over is greater than or equal to 0. Simplifying, we get a minus 2 plus 1 over is greater than or equal to 0. Adding 2 to both sides, we get a plus 1 over is greater than or equal to 2. And this completes our proof of the first part of the theorem. Let's visualize this inequality with a graph. We'll plot the function f. A equals a plus 1 over a for values of a greater than 0. Notice that the function reaches its minimum value of 2 when it equals 1, and as it moves away from 1 in either direction, the function value increases. This confirms our theorem. A plus 1 over a is always greater than or equal to 2 when it is greater than 0, with equality when it equals 1. Now, let's look at the second part of the theorem. If it is less than 0, then a plus 1 over a is less than or equal to negative 2. Let's prove this second part of the theorem. Similar to before, we start with the expression a plus 1 squared is greater than or equal to 0. This is true for any real number. We expand this to get a squared plus 2. A plus 1 is greater than or equal to 0. Now we divide both sides by a. But this time, since a is negative, dividing by a reverses the direction of the inequality. So we get a squared over a plus 2. A over a plus 1 over a is less than or equal to 0. Simplifying, we get a plus 2 plus 1 over a is less than or equal to 0. Subtracting 2 from both sides, we get a plus 1 over a is less than or equal to negative 2. And this completes our proof of the second part of the theorem. Let's visualize the second inequality with another graph. We'll plot the function f. A equals a plus 1 over a for values of a less than 0. Notice that the function reaches its maximum value of negative 2 when it equals negative 1, and as it moves away from negative 1, the function value decreases. This confirms our theorem. A plus 1 over it is always less than or equal to negative 2 when it is less than 0, with equality when it equals negative 1. Now, let's combine both parts of the theorem to state it more generally. If it is not equal to 0, then the absolute value of a plus 1 over is greater than or equal to 2. This theorem can be extended to more general rational expressions. If a and b are non-zero numbers with the same sign, then a over b plus b over is greater than or equal to 2. We can extend this even further. If a and b are numbers with opposite signs, then a over b plus b over a is less than or equal to negative 2. To summarize what we've learned, 1. If it is greater than 0, then a plus 1 over is greater than or equal to 2. 2. If it is less than 0, then a plus 1 over a is less than or equal to negative 2. 3. More generally, if it is not equal to 0, then the absolute value of a plus 1 over is greater than or equal to 2. For 4 rational expressions, if a times b is positive, then a over b plus b over is greater than or equal to 2. 5. If a times b is negative, then a over b plus b over a is less than or equal to negative 2. This theorem is a beautiful example of how algebraic manipulation and geometric visualization can help us understand fundamental properties of numbers and their relationships. Welcome to our lesson on basic inequalities. Today, we'll explore and prove 3 important inequality theorems that are fundamental to mathematics. Let's start with our first inequality theorem, which states that a squared plus b squared is greater than or equal to a times b. This inequality is very useful in various mathematical contexts. Now, let's prove this inequality. We'll start with a very important property. The square of any real number is always greater than or equal to 0. So, the square of the difference a minus b is greater than or equal to 0. We also know that a squared plus b squared is greater than or equal to 0. Adding these two inequalities together, we get a squared plus b squared plus the square of a minus b is greater than or equal to 0. Let's expand the expression a minus b squared. When we expand this, we get a squared minus 2ab plus b squared. Substituting this back into our inequality, we get a squared plus b squared plus a squared minus 2a b plus b squared greater than or equal to 0, which simplifies to 2a squared plus 2b squared minus 2a b is greater than or equal to 0. Dividing both sides by 2, we get a squared plus b squared minus ab is greater than or equal to 0. Rearranging, we get a squared plus b squared greater than or equal to ab, which proves our first inequality. Let's move on to our second inequality theorem, which states that a squared plus b squared plus ab is greater than or equal to 0. This is another important inequality with wide applications. Now, let's prove this inequality. Similar to our previous proof, we'll use the property that the square of any real number is greater than or equal to 0. In this case, the square of a plus b is greater than or equal to 0. And as before, a squared plus b squared is greater than or equal to 0. Adding these inequalities, we get a squared plus b squared plus the square of a plus b is greater than or equal to 0. Let's expand a plus b squared. When we expand this, we get a squared plus 2ab plus b squared. Substituting this back into our inequality, we get a squared plus b squared plus a squared plus 2ab plus b squared is greater than or equal to 0, which simplifies to 2a squared plus 2b squared plus 2ab is greater than or equal to 0. Dividing both sides by 2, we get a squared plus b squared plus ab is greater than or equal to 0, which proves our second inequality. Now let's move to our third inequality theorem, which states that a squared plus b squared is greater than or equal to 2 times ab. This is known as the AMGM inequality for two numbers and is extremely important in mathematics. Let's prove this inequality. We start with the fact that the square of the difference, a minus b, is greater than or equal to 0. Expanding this inequality, we get a squared minus 2ab plus b squared is greater than or equal to 0. Rearranging, we get a squared plus b squared is greater than or equal to 2ab, which proves our third inequality. Finally, it's important to note that equality holds in all these cases when a equals b equals 0. This is when both variables are 0. Let's visualize this with a graph to better understand these inequalities. Welcome to our mathematics video. Today, we'll be looking at basic inequalities, specifically Theorem 3, and walk through its proof step by step. Here's the inequality we'll be proving today. 1 over a plus 1 over b is greater than or equal to 4 over a plus b, where a and b are both positive. Let's begin our proof. We'll follow the exact algorithm as shown in our reference material. We begin with the AMGM inequality, which states that for positive numbers, the arithmetic mean is greater than or equal to the geometric mean. In our case, we can say that a squared plus b squared is greater than or equal to 2ab. For the next step, let's add 2ab to both sides of the inequality. We get a squared plus b squared plus 2ab is greater than or equal to 2ab plus 2ab. The right side simplifies to 4ab. Now, let's recognize that the left side of the inequality is actually the square of a plus b. So we have a plus b quantity squared is greater than or equal to 4ab. Now, we can rewrite this by expanding the left side. We get a plus b times a plus b is greater than or equal to 4ab. For the next step, we'll divide both sides by a times b times a plus b. This gives us a plus b times a plus b divided by ab times a plus b is greater than or equal to 4ab divided by ab times a plus b. Now, we can simplify both sides of the inequality. The left side becomes a plus b divided by ab, and the right side becomes 4 divided by a plus b. Let's further simplify the left side. We can rewrite a plus b divided by ab as a over ab plus b over ab, which simplifies to 1 over b plus 1 over a. Finally, we can rewrite this to match our original theorem statement. We get 1 over a plus 1 over b is greater than or equal to 4 over a plus b, and thus, we have proven the theorem as stated. It's important to note that equality holds only when it equals b. In that case, both sides of the inequality would be equal to 2 over a. The image also shows a second theorem. A squared plus b squared plus c squared is greater than or equal to ab plus ac plus bc. We won't go through the full proof for this one today, but it's a related inequality that follows similar proof techniques. We need to prove that a squared plus b squared plus c squared is greater than or equal to a times b plus a times c plus b times c. This is a famous inequality that has applications in various mathematical fields. Let's start our proof. First, we'll rearrange the inequality by moving all terms to the left side. We get a squared plus b squared plus c squared minus a b minus a c minus bc is greater than or equal to 0. Step 2. To make the next steps easier, we'll multiply both sides of our inequality by 2. This gives us 2 times the expression. 2 times a squared plus 2 times b squared plus 2 times c squared minus 2 times ab minus 2 times ac minus 2 times bc is greater than or equal to 0. We can simplify this as 2a squared plus 2 b squared plus 2c squared minus 2 a b minus 2 ac minus 2 bc is greater than or equal to 0. Step 3. Now, we'll regroup the terms to create perfect square expressions. We can rewrite this as open parenthesis a squared minus 2 a b plus b squared close parenthesis plus open parenthesis b squared minus 2 bc plus c squared close parenthesis plus open parenthesis c squared minus 2 a c plus a squared close parenthesis is greater than or equal to 0. Step 4. Now, we recognize these as perfect square expressions. We can rewrite this as open parenthesis a minus b close parenthesis squared plus open parenthesis b minus c close parenthesis squared plus open parenthesis c minus a close parenthesis squared is greater than or equal to 0. Step 5. Since squares of real numbers are always non-negative, this final inequality is always true. The sum of 3 squared terms is always greater than or equal to 0. Therefore, our original inequality a squared plus b squared plus c squared is greater than or equal to ab plus ac plus bc is proven. Now, let's investigate when equality occurs. The equality occurs when all the squared terms equal 0. That is, when a minus b equals 0, b minus c equals 0, and c minus a equals 0. Solving these equations, a equals b equals c, and c equals a, we conclude that equality holds when a equals b equals c. In other words, all 3 variables must be equal. Welcome to this educational video on basic inequalities. Today we're going to explore Theorem 4, which is a fundamental inequality in mathematics. This theorem states that if a plus b plus c is greater than or equal to 0, then a cubed plus b cubed plus c cubed is greater than or equal to 3 times a times b times c. Let's display this theorem formally. Let's look at an example to understand this theorem better. For our example, let's set it equals 1, b equals 2, and c equals 3. First, let's check the condition. We need to verify that a plus b plus c is greater than or equal to 0. In this case, 1 plus 2 plus 3 equals 6, which is greater than 0. So our condition is satisfied. Now, let's check if the inequality holds. We need to calculate a cubed plus b cubed plus c cubed and compare it with 3 times a times b times c. The left side is 1 cubed plus 2 cubed plus 3 cubed, which equals 1 plus 8 plus 27, giving us 36. The right side is 3 times 1 times 2 times 3, which is 3 times 6, equal to 18. Since 36 is greater than 18, the inequality holds for our example values. Now, let's explore the proof of this theorem. We begin with a remarkable identity. The left side of our inequality, a cubed plus b cubed plus c cubed minus 3abc, can be rewritten as 1/2 times the sum of plus b plus c multiplied by the sum of squares of differences, the square of a minus b plus the square of b minus c plus the square of c minus a. This identity is key to our proof. Let's take a moment to understand it. Now, let's analyze this identity step by step. First, notice that the expression in the square brackets is always greater than or equal to 0. This is because it's a sum of squared terms, and squares are always non-negative. Next, recall our condition. A plus b plus c is greater than or equal to 0. Since we have a product of 2 non-negative terms, their product is also non-negative. Therefore, a cubed plus b cubed plus c cubed minus 3a bc is greater than or equal to 0. Rearranging, we get our theorem. A cubed plus b cubed plus c cubed is greater than or equal to 3abc. Let's also look at some special cases mentioned in the note. First, if a plus b plus c equals 0, or if a equals b equals c, then a cubed plus b cubed plus c cubed equals 3abc. This means the equality holds in these cases. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.